You're ready to graph Hooke's Law lab, so I want to go over just a few things that might help you out. So you measured in centimeters the amount of stretch you got. Assuming you measured correctly, you probably have a number down here ranging from maybe 10 centimeters of stretch to maybe higher depending on the rubber band you have, maybe even up to 20 centimeters or so. So what I'm going to do is let's just assume that you had about a total in the end of maybe 15 centimeters of stretch. So how are you going to go about graphing this? So what I would do is you always start by putting your independent variable down here. So your independent variable is going to be the mass, which we adjusted by putting different amounts of water in there. So we could put the units as grams, even though we measured it in milliliters, because every gram of water, or every milliliter of water, has a mass of a gram. And then stretch is going to go over here, and you measured that in centimeters. Usually for the title, you include the two variables. So something like how mass affects the stretch of a rubber band, or something like that. Okay, so how do we go about putting our numbers on our graph? You always start at 0, and you would do that for both x and y axis. And then you just simply find the largest number you have to graph. So the largest number you had to graph for mass is 350 grams. And so you got to start at 0, and you want the 350 to show up somewhere over the halfway point. So if I count by tens, I'm just going to try something. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130, 140. I don't think I'll make it. So you could count maybe by 15s and make it, which is kind of an awkward number to count by. But I think it would work. I'd have to do it to be sure. Let's just see what happens if you count by 25s. So that'd be 25, 50, 75, 100, 25, 50, 75, 200, 25, 50, 75, 300, 25, 50, 75, 400. So I actually think counting by 25s would work. 15s might work, but you'll have to double check that, okay? 15s might be better because it would stretch it out a little more, but the 350's over the halfway point, so we should be okay with that. And then what about for the y-axis? Well, you have to see what your highest number is. I can't solve that for everybody, but let's just assume it's 15. If it's 15 or somewhere in that range, and you got to count by something to get the 15 somewhere up here. So maybe for me it might be just counting by ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that actually works counting by ones, and I'd label those all the way up because the 15 is higher. If you stretch by like over 20 centimeters, you might need to count by 2s instead of 1s or something like that. Okay, then you're just going to put a data point for every one of these. So all your spots would have a data point. So you'd put 25 and whatever the stretch was, and 50 and whatever the stretch was. And you put all your dots on here. Before I talk about that, probably most of you thought what would happen in this lab is that you would end up with some sort of straight line going up the graph. That's probably what your hypothesis was. It's probably not what actually happens in the lab, though. So what actually happens in the lab? This is probably what you thought would happen before you started the lab, and it's unlikely that you get these exact results. It was probably, the rubber band is not perfectly elastic. It's actually harder to stretch at the beginning, and it stretches pretty smoothly, or is pretty close to perfectly elastic, usually towards the middle of the stretch, but as you get towards the end, it gets harder to stretch again. So without having seen your data, and there could be some exceptions to this depending on the rubber band, you probably got data that looks something like this. I'm just going to put some random marks on here. Something like that. And you probably don't want to just draw a straight line on those. You're probably going to want to do something like this. So let me draw in red what actually happens here. And this part of your rubber band actually follows Hooke's law. It's perfectly elastic, meaning every time I add even amounts of mass, it stretches the same amount. But you can see at the beginning of the stretch, it was harder to stretch, and at the end of the stretch, it was harder to stretch. And so it does not totally follow Hooke's law. Most things in real life don't completely follow Hooke's law because they are not perfectly elastic.